So welcome. We're delighted to welcome you today for our CIS Get to Know Your Neighbor seminar, purely online this time. We're delighted to have Professor Pascal Fua with us. Pascal is a full professor and head of the Computer Vision Laboratory here at EPFL. His talk is entitled Deep 3D Surface Meshes. We have approximately 1 hour for the seminar. The talk will last 40 to 45 minutes, and then we have time at the end for Q&A. Feel free to put any questions you have during the talk in the chat, and either Pascal will take them up during his talk, or we will take them up at the very end. Before we start, big thanks to you, Pascal, for your availability, and to the entire CIS team for organizing this event again. Now, Pascal, the screen is all yours.
Thank you. So, as Jan said, what I do for a living is computer vision. So first, I should maybe try to define what this is. And the basic idea is you take a video sequence like this one, in this case, a baseball, that is thrown very, very hard against something that looks like a baseball bat. And the game is to try to model what happened. So here's an image from the video sequence. What we do is we have a model of the baseball bat before it hits, just a sphere. We deform that sphere so that it projects at the right place in the image. That's the red mesh that you see on the lower left. And from this, we can infer the 3D shape, can get back the third dimension that was lost when you acquire the image. And if you do this over the whole sequence, what you get is a 3D reconstruction of what happened. So you can think of computer vision as inverse computer graphics. My colleagues who do computer graphics would maybe start with a 3D reconstruction and produce a realistic video. We do the reverse. We take the real thing and we build a 3D model. Now, you might wonder, why am I modeling baseballs? Because, well, it's not really a popular sport in Europe. And the reason is that we had a collaboration with mechanical engineers at Washington State University. And these guys are the Baseball Lab of America. And they are indeed very interested in what happens when a bat hits a baseball. And one of the problems they're facing is it's actually hard to simulate, and their simulations are not quite right. So they are interested in us, telling them, well, okay, here is what really happened. Your simulation should produce something similar. And so this is, to them, this is a tool they can use to refine their simulation algorithms. So we've done quite a bit of that over the years. So for example, we've done a lot of modeling sails. So this all started many years ago with Alinghi. And this is a different boat that did the Vendée Globe. And the Vendée Globe is a race around the world where you have one sailor who is going to manage his boat for, well, 70 to 80 days. And no one can do this at peak efficiency the whole time. So the idea was to track the motion of the sail and give indications to the sailor, and maybe at some point even do some, you could imagine a robotic sail that would adjust itself, that would trim itself. And I don't know if, so this, for many reasons, we weren't able to do this, but we've heard that Alinghi will sail again, and we would be very, very happy to be part of that particular game. And I'm coming to what I really want to talk about today. We've spent many years developing algorithms that can be used to reconstruct 3D surfaces from images. And relatively recent, and these algorithms are based on explicit surfaces. So you've seen that what we use to represent the surfaces are 3D meshes. Essentially the same thing that most graphics algorithms are based on. And there is a very good reason for that. They are very versatile. You can model many, many things with them. They are really a good tool. They have one problem, which is once you've decided on the topology of your mesh, the 3D mesh, it's kind of hard to change it. Especially if you want it to change to be differentiable, which is important as soon as you talk about deep learning, which we talk about a lot these days. So another a competing approach to this is instead of representing surfaces as 3D meshes, you can represent them as what's called implicit surfaces. So you define what's called an implicit field, and the surface is going to be a zero crossing of that implicit field. And the advantage of this is that this is a way to model surfaces whose topology can change. So this is, in fact, a fairly old idea, like a lot of what we're doing right now, because deep nets are also a very old idea. But until recently, it was viewed as fairly impractical because to represent surfaces this way, you had to represent a cube. You put the object you want to model in the middle of a bounding box, and then you have to discretize this bounding box very finely, and that's terribly expensive. So that was the view until 2 years ago, when some smart people realized that you did not need to represent the box explicitly. You can use a deep net to do that. So let me describe this in a bit more detail. So when the typical tool to do this is what's called a signed distance function. If you have a surface, which is here represented by the green line, you can define a function that is the distance, that green line, and you make it negative inside and positive outside. So either the negative or the positive distance, which is why it's called a signed distance. And if you do this, your surface is the place where the distance is zero. So formally, what you define is a function f that goes from R3 to R. So why R3? Because the drawing is in 2D, because I don't know how to draw in 3D, but we are really talking about 3D surfaces. So it's a function f from R3 to R, where f is the signed distance to the surface. And the point of this representation is if you change the value of f, you can change the surface, and you can also change its topology. You can change the shape of the surface, and you can also change its topology, which is a lot harder to do with other kinds of representations. So, as I said, this is an old idea, but until recently, it was not viewed as being practical because you had to store all the values of f, so have discretize R3 very finely, and that very, very quickly becomes very, very expensive. So what changed this is the realization by, among other things, these guys in 2019, that one way to do this is to train a deep net to take as input x, which is a point in space, and return the value s of the signed distance. So you don't have to store that signed distance anymore. You just have to store the weights of the network, but we're used to doing that. And it is a network that computes S. And you can go one step further by making this conditional on what I'm going to call a code C. And this is a conditional signed distance function where it takes an input, the C. For every point x in space, it returns a value of s, the signed distance. And if you change C, you will change f, and therefore the shape of the surface you describe. So now you have a 3D surface that's described in terms of a code C. So this is very, very nice, but there is one bottleneck that remains. That is, if you need a 3D surface, an explicit mesh, for example, and I'll show examples later in which you actually need them, you have to run an algorithm that's called a Marching Cube algorithm, which is not differentiable and oftentimes very, very slow, which means it's not easy to incorporate that in a deep network architecture. And this is one of the problems we've tackled. Maybe before I go much further, this way of representing things is at the heart of everything I'm going to say next. So if there are any questions about that, now would be a good time to ask them. All clear? That's really where Zoom, you cannot look at people in the eyes and no? Okay, so I'm going to assume that this is crystal clear, everybody's understood, and I'll move on to our solution to this problem. So when you are in a deep learning pipeline, typically what you do is you minimize a loss function, L, which is a function of the vertices and the facets of your representation. So you do a forward pass, which means you take your implicit representation, you run Marching Cube, which is not differentiable, that gives you vertices and facets, and then you compute your loss function. So the forward pass is not a problem. The problem is going to be the backward pass. When you train your deep nets, you need to compute the derivative of L with respect to C, the code. And you just use the chain rules as a sum of dl dv, v the vertices, dv ds, and ds dc, since s depends on c. And there you run into a problem. The problem is because Marching Cube is not differentiable, dv ds is not easy to compute. It doesn't exist. And you cannot naturally incorporate that into your deep net architecture. But, and that's where our contribution is, let's remember that f approximates a sign distance function. So we can do a bit of geometry. And actually, one of the reasons I'm presenting this is even in the era of deep networks, some understanding of geometry and optimization are useful, which is something that we try to drill in the head of our students. So more specifically, what you can prove is that if you go from S to S plus delta S, or small, an infinitely small change of S, in fact, because the normal to an SDF is just its gradient, you can in fact compute its derivative. dv ds exists, and it is minus the normal to the surface at that point, which is the gradient of the surface. And if you are interested in the actual proof, I will refer you to the paper. And in fact, it can be extended to things that are not sign distance function. You can show that if the function is simply continuous and differentiable, then this dvds has a slightly more complicated expression, but it can be computed. And in fact, if you look at this, when S is a sign distance function, this is 1. So these two definitions are compatible. So in the end, what you have is that this term, this derivative that was hard to compute, is in fact, once you've done the math, not a big deal. You can compute it algebraically, and you can stick it into your deep net. So in practice, what this lets us do is you can take a mesh that, for example, is a sphere coded by some code C0, And you can continuously and differentiably turn it into a torus. So why a torus? Because it doesn't have the same topology. This is genus 0. This is genus 1. And yet we can do a smooth transition from one to the other by, we start with a code C. We use the Martin cube algorithm to compute the mesh and the vertices. We use them for the forward pass and for the back propagation using the formula that was on the previous slide. We update the code and we iterate. And in this way, we go from here to there, or from a cow, genus 0, to a duck, genus 1. And at all points in this transformation, we have a continuous mesh. Okay? Okay, that's all for the math. Again, I ask, now I'm going to show how we can use this. It's a nice tool, but before I explain what we can do with this, any questions so far? Nope. Okay. Yes?
No, I was just suggesting, just raise your hand or unmute directly. We are at an internal seminar to ask you a question.
Yeah, or even better, type your question, and I have the chat window open, so I'll see it. Okay, so I'm a vision guy, well, at least I claim to be. So one obvious application is to reconstruct 3D objects from images. And the idea here is we are going to train a deep net to associate to images a code. So this is using what's called an autoencoder, which we create a code, and then when we feed it to the thing that construct the surface, F theta, we get a code that will generate images that look like the original ones. And once we've done that, we can use this to do what's called a generative model, which means we have a code, we crank it through the decoder that will render an image, and we can then optimize on C so that the image that's produced is as close as possible to a target image, meaning that we have properly reconstructed in 3D. So here's an example. We start with an image of a chair. We compute an initial code that gives something that's quite rough, but we can then refine it to produce a 3D model of that chair that's quite good. So remember, all we had was this image, and from this, it reconstructs something that looks good from the original viewpoint, but also from a very different viewpoint, which is a good indication that we have properly recovered the geometry of that chair. And of course, there's somewhere some numbers that say that we do better than the competition, because this is why this task, because it's a standard benchmark task. Okay, so this is, do you hear the comment on the video or not? There's sound on this video. I don't know if you hear it.
It's not very strong, Pascal.
It's not very strong. Okay. So I'm going to talk over it. So here is what we can do with this. And the idea is to make a tool that allows someone to sketch. So you sketch in 2D, the thing produces a 3D model, and then you can then modify it interactively. So the black line is an indication by the designer that he wants a different shape. So same idea, you sketch in 2D, you get a 3D chair, and I'm going to move one of the feet. And the chair deforms in 3D to match the sketch, and you can notice that it stays symmetric because it has a prior that says that chairs tend to keep their feet symmetric. Now we're going to play a slightly different game. We are going to sketch, we're going to lower the armrests by sketching. And we can do that several times. And something interesting is going to happen when we lower them enough, which is the topology hasn't changed, but at some point, if we make them too low, poof, the armrests have disappeared. It's the same as the power example. It has changed topology without drama, without fuss, and without loss of differentiability. And this actually is valuable in a tool of that nature. Okay, so one question is, are the priors imposed by the user or learned by the network? They are learned by the network because it had a database of chairs to learn this representation and use it. So in the database it had, all the chairs were symmetric, so it has learned that chairs should be symmetric. Of course, you could put in the database broken chairs, in which case things would happen differently. And that actually illustrates the fact that in deep learning, the technique is well and good, but the database you use to train is primordial. And so the follow-up question is, can it rise from a chair to a sofa? We haven't tried, but I doubt it. You would, I mean, it could, but you would have to have sofas in your training database. Otherwise, okay, so this was what I just showed was essentially what you need to do to get your paper published in a good venue, because this is the benchmark application, and I'm not sure it's incredibly useful, but so let me now show one that is truly useful and on which we are working fairly intensely these days, which is 3D shape design. So let's say you are a car manufacturer or a car designer, and you want to design a race car. So typically what you're going to do is you're going to design a shape on your computer. You are going to run that into a simulator. Usually it won't be good on the first try, so you will redesign and iterate this process until you have something you like. So this works. Obviously, we have cars, we have planes, but it's slow. It's very, very time consuming because designing takes time, running the simulation takes time, so the number of iterations you can do in a day is very low, or in a week even. So there's been much interest in trying to automate this process. And one popular method in the CFD community to do this is to use something that's called Kriging, or Gaussian processes for computer scientists. And the idea is as follows. You want to do, say, CFD, so you have a CFD simulator, doesn't matter which, use your favorite one. Create a database of objects that more or less represents what you're interested in. Compute, run your simulator on them, and compute the physical quantities you're interested in. It could be drag, it can be pressure. In this case, they're pressure fields. And from this, you compute a quantity measure like drag, for example, what you want to minimize. And what that allows you to do is to create what's known as a response surface, meaning that you have the little red cubes represent samples, so shapes for which you have a simulation value. And you can guess what the values are going to be for other shapes for which you have not run a simulation by nonlinear interpolation, so that you can find a potential optimum without running any further simulations. And typically, what's being used to do this is what's called a Gaussian process. So Kriging and Gaussian process are synonymous, and it works nicely, but it only can deal with models that have relatively few parameters, I mean 20, 30. After that, you're on very high dimension, and the GPs tend to choke. So what can you do about this? Well, you can remember that we have these wonderful deep nets. And what do deep nets do? Essentially, they do nonlinear interpolation. I think that I'm not sure I'm right, but that's the way I think about them. They are powerful nonlinear interpolators. So they're extremely well suited for this task. And you can compute your response surface using not GPs, but instead convolutional neural networks, and more specifically, geodesic convolutional neural networks. Why geodesic? Because you need a neural net that operates not on an image, but on a 3D mesh that represents a physical object that can be irregular. And the big advantage of neural nets for this particular application is they can tolerate as many parameters as you want. So if you want, you can make every vertex, the 3 coordinates of every vertex of your mesh a parameter, and it will still work. So here is the kind of network we use. I'm probably not going to get into detail, but it's fundamentally some form of a ResNet. And here's what it does. So we have a collaboration with Airbus, and here is half of an Airbus. And you can run a full simulation. It will take 1 hour to get a decent result. And or once it's been trained, we can use our GCNN, which will yield a prediction in 30 milliseconds, so much faster. And it's extremely similar. So what I'm showing here is the pressure fields around a wing. And the GT, the red curve, is what we get from simulation. The others is what we get from our network. They are very, very close. And relatively reassuring, that remains true in more challenging cases where here we were simulating what happens in a transonic regime where things start to become nasty, and it still yields very good accuracy. So how do we use this now? Well, what we have now is that we have a way to predict something of interest, like drag in the case of the car, using a deep net, which means it's differentiable. And so we have what I'm calling D, which is a deep net, that computes the drag from directly from the 3D mesh, and it is a differentiable function of these vertices, which means we can optimize. So here's what's happening. We have a surface that is wrapped around an incompressible sphere. And the system is optimizing the shape of the surface so that the resulting shape has a minimal drag. So it comes up with this funny shape with this long tail, which I don't know if it's strange or not, but if you've ever seen bike racers who compete on speed racing, they have helmets with these long tails, because they are trying to solve a very similar problem. Enclose a spherical thing, their head, in an aerodynamic shell. So that makes me think this is actually a reasonable answer. And we can go to more realistic objects, like, for example, this drone. This is a drone built by SenseFly, which is a spin-off of one of Dario Florido's lab. And this is it's a very good drone. It flies very well, but the aerodynamics are not really optimized. I mean, the wing that's being used is a very simple shape, which means it tends to drag. And it will fly nevertheless, but it will consume more energy than is strictly needed if the performance was better. So we've been playing at using algorithms to start from the original drone, which has an L over D. L over D is lift over drag. It's a standard measure of the effectiveness of a wing of 11.9. We can deform the wings to improve that. And if we are allowed, while we are at it, we can also deform the whole thing. So not only the wings, but also the fuselage, so that it's even better. So of course, there's a constraint. The fuselage still has to contain all the onboard electronics and the autopilot and the engine and everything else. But under these constraints, we can further improve the behavior. And so this was the simulation. Well, SenseFly has gone through many trials and tribulations recently, so we haven't been able to convince management to actually build it. But in practice, we have worked with these guys from ANSI, who have been building this this bike. Doesn't look like it, but this is a bicycle. It's actually once painted, looks like this. This is a reclining bicycle. The two people are the bikers. And the way it's used, they climb into this and their head is here, their bottom is here, and their feet are here, and the pedals are here. And so the game was, it was just before COVID, to Jan is asking what was the idea for the highly optimized SenseFly drone body. To be honest, I didn't put it because I don't remember, but I can.
I was just curious. Sorry.
So they went to this place in Nevada where they have this 5-mile long road, and so it's 5 miles, so 8 kilometers long, completely straight, completely flat, and they pedal as hard as they can, and they are being clocked on the last 100 meters. And well, they went pretty fast. So they beat a couple of world records. 136 kilometers on a bike. I mean, it's not an electric bike, right? It's human power alone. It's pretty damn fast. And well, there are lots of things that have to go right for something like this to happen, but the aerodynamics being good was one of them. Okay, and this actually was done without priors. So in this case, the optimization was done strictly directly on the 3D vertices of the mesh. But for most application, you really want a prior of some sort. So we are back to the SOFA question, except now we are talking about cars. And what we did is train a network to recreate a database of cars. So for each code C, you crank it through a network, it produces an implicit function F, and you make it so that for an appropriate value of C, the surface that you get can approximate each one of the individual cars in your data set. And what you get in the end is something that's going to allow you to model all the cars in your data set and everything in between. So you're essentially going to interpolate between all these cars. And you can notice that these cars have different shapes, right? It's not only one type of car, so there is a fair amount of distributed power in these things. So now that we have that, we can go back to our drag minimization problem. We have a code. We have something that converts this into a 3D shape in a way that is differentiable. And then we have our GCNM that takes the 3D shapes and computes the drag. So we can minimize the drag of C with respect to C, with respect to the code, under a number of constraints, and typically is you want to leave some space for the passengers and the engine. And that's how we take an ugly SUV and we turn it into, I don't know if it's ugly or not, but into something that's far more aerodynamic. And one of the reasons I'm showing all these car examples is because, in fact, we have a spin-off company called Neural Concept that does this for real, and their main thrust is the car industry. They're really interested in this stuff. As before, we can also try to design interfaces for graphics designer. So the idea here is they have a demo now that you sketch a car on an iPad, and it'll produce the car that looks like your sketch, and at the same time is aerodynamic. And the target user for this is your typical designer, who's usually an artist, not an engineer. So he knows what he wants it to look like. It's very useful to give him some tools to guide from the aerodynamic point of view as well. How close is it? So there was a question, how close is a giant car to something in the database? Not that close, in fact, surprisingly, because the database is not that huge. And it does decent interpolation. So this actually, I mean, you can be, Bruno says he's obsessed with generative approaches. I am too. And there is, I think, a very interesting research question to which I don't have the answer, which is, what is the space of cars this thing can model, given a database? In a sense, it's presumably the convex envelope of all the cars it has seen, but this is poorly defined, and this is definitely something we should look at more carefully. So how are the priors? Another question is, how are the priors embedded in the NN? So the answer to that was here. We trained it. So we use what's called an auto-decoding approach that learned at the same time the weights of the network, and it learns a code for every car in the database. And at the same time, it learns a network that allows it to do it. So the network the priors are essentially embedded by the set of cars you give it to work with. Okay. So what I've shown so far are not really cars. They are outside shells. But a real car is more complicated than that. Typically, you want a CAD model where you have the body of the car, and then the wheels, and then the rear view mirrors and everything else. And what we are currently working on is expanding this approach so that can handle more significant primitives or groups of primitives. So in this case, a free form for the body of the car and cylinder-like shapes for the wheels. And the kind of constraints we want is the wheels should not, of course, touch the body. And that actually works, so we can optimize in the same way. And we also get optimization results where now the difference between what I'm showing now, what I showed before, is now the wheels are clearly separated from the body and they don't touch the body, which presumably will give you a car that will work better. And just so that you don't say that I'm obsessed about cars, here's an example from a different field where this is what's called a water mixer. So a water mixer is something you pump liquids at one end, different liquids. You rotate something by this helix, and at the other end, they are well mixed. And this is typically made of, in the middle is the central helix, which is encased in a cylinder with things at the top for connection and waterproofing. So we can model this in terms of a series of primitives. So not only the kind of surfaces I've talked about until now, but also more geometric primitives, because when you start building things, you have lots of cylinders and squares and geometric shapes that you know, and you want these things to all interact with each other. So that allows you to do things like this, where in this demo, I'm changing the width of the tube and the shape of the ellipse inside adjusts automatically. Or you can change the topology of the ellipse, of the helix, under the constraint that it must still fit in the tube. So this is actually a powerful modeling scheme in which we are actually working. So here's another example of this is you can take one car and change the wheels. So you want to move the wheelbase and the rest of the body will adjust to accommodate that while retaining the same overall general shape. And this is actually not limited to manufactured objects. We are working, for example, we have an InnoSwiss project in which we want to model the heart. And we are going to use exactly the same techniques to model the full chamber of the heart and to impose the fact that in a functioning heart, the various chambers have to connect in a very specific way. They cannot be occlusions, otherwise it's not a working heart. So this kind of optimization approach under constraint, I think, is a very good framework to do this. So in maybe before I conclude, let me see what the questions are. Okay, so Jans Kalud is asking whether that would apply to general surface modeling, and that's an excellent question because that's exactly what we're working on with irregularities. Is what we want to guarantee is that the surfaces we produce are manufacturable. I mean, if I show you an example, a surface, we can all tell, oh, this looks like a manufactured object or this doesn't. And one of the things we are looking at is using adversarial training to guarantee that the surfaces we produce are either smooth or with sharp edges the way manufactured objects typically are. So I hope I answered the question. So the short answer is yes, it will generalize, we hope. And are the extrapolation trials deterministic? Well, as everything in deep nets, no, it's not deterministic because there's always a bit of randomness at the beginning, but it seems to be fairly stable because we run many, in the papers, we do have variance and it seems to be reasonably stable. Okay, so in conclusion, what I've shown is that we can combine explicit and implicit representations and that gives us the ability to exploit the strength of both representations. So what we use are what's called deep sign distance functions that can be used to implement 3D meshes that can change the topology, and we can make the whole thing differentiable. And this opens the door to many applications in fields like, well, computer-assisted design, which I've shown, medical imaging, which I've hinted at, and also in the area, I'm not sure I have the slide here, sadly, but one of the things we are also looking at is designing surfaces that are not only aerodynamically efficient, but also are easy to control. So typically, vertices can correct me if I'm wrong, but control is typically handled by, I give you an object and you design a control policy that will make it do what you want it to do. What we are saying is we can maybe do a bit even better than that. We can design the object from the get-go so that it's easy to control, and design the control policies as are come naturally. And our plan is to demonstrate this by designing a glider, a robotic glider that will do dynamic soaring. So dynamic soaring is a crazy form of flying where you exploit differences in wind speed to gain speed, and they have these unpowered things that go 500 miles an hour or 800 kilometers an hour, no engine. And of course, it'd be fun to go even faster. So of course, as usual, this is not my work. This is a work of a lot of people, and I thank them. Okay, I think that's it.
Thank you very much, Pascal. The next Get to Know Your Neighbor seminar is with Professor Alexander Mellis. That's in 2 weeks' time. And then just this Wednesday, you have the opportunity to listen into what Michele Giarotti works on at the EPFL Reagan AIP seminar series at 10 a.m. European time. And we are looking forward to welcome you soon again. Thank you so much. Stay safe and take care. Bye.
Bye.